When I was a kid, I used to watch rocket launches on loop. Let's be honest, I watched them mostly because I thought they looked awesome. Launches are big public shows, and today with high definition and even 4K live stream, they are more spectacular than ever. Tell people you build rockets, and they're usually blown away. The first thing they picture? A spaceship with a giant flame underneath. Because that's what they've seen on TV and in movies. But even back then, those live streams had something else. Less fancy maybe for casual viewers, but way more valuable for us enthusiasts, the numbers. Because like any nerd in any hobby, you have to flex on your numbers. And at school, we had a motto that fit perfectly. We go faster and higher than anyone else. Even back then, agencies got it. They dedicated a little corner of the stream to show the launcher insane speed and the altitude only a rocket could reach 6. And when they wanted to show they were changing the game, they packed their stream with more info and better quality, for both the public and the nerds. Sure, sometimes the numbers are a bit message, pre-recorded even, especially in countries that aren't exactly on friendly terms with failure, but in most cases, the data is real, and it's often the key to understanding what went wrong.
Taken.
10, 9, 8, 7, 6, 5, 4, 3, 2, unité, feu. Allumage. Décollage. Tous les paramètres propulsifs sont normaux et la trajectoire est normale.
When you launch something as complex as a rocket, you have to expect things to go wrong. And since you're reaching absurd speeds, if anything fails, what's left of your rocket becomes a rain of molten metal, scattered across the air. So pretty quickly you realize something. If you want to understand what happened, the simplest way is to send the data directly to the ground, to your control room. Here's the thing, once the rocket is gone, the control room doesn't control anything anymore. The only thing you can manage are the data being received and the moment you decide to blow it up, or in some cases, cut the engines. And to manage that data from the ground, we use the telemetry. Let me give you some background. 4 years ago, I started a video series about mini rockets, high-power rocketry, and embedded electronics. 3 episodes came out, and at the end of the last one, I teased the 4th, about telemetry.
On en parlera dans la prochaine vidéo.
4 years! It took me 4 years to build a decent telemetry. That alone should tell you something. In amateur rocketry, telemetry isn't mandatory. You can totally get by on board recording, an SD card or a flash chip. Flash has one big advantage. It's less sensitive to vibration, so you avoid finding your SD card snapped in two after an overly enthusiast landing. In amateur build, rockets often fall back into a roughly predictable area. Sometime in one piece, sometime not. But sometime telemetry is all you'll recover from your rocket. There's no guarantee you'll ever find where it landed, parachute or not. And even if you know exactly where it is, you might not be able to get there. Shout out to the space minefield, really is in the middle of the range. And in that case, your data is gone forever. If we hadn't had a reliable telemetry, we'd have gotten nothing from Belisama 2033 flight. Thanks to that data, we presented at the Space and Industry Prize and learned a ton from the rocket's flight behavior, including some false sensor reading. Check out those videos if you haven't. And beyond rockets, telemetry, using the radio technology, is a fantastic way to get all sorts of data remotely. But to stay in the hobby category, this is great for tracking a weather balloon, recover a drone, monitoring an RC plane, and it's the same principle that lets us talk to nanosat, CubeSat, rovers, probe. In short, telemetry is a superpower, the ability to transmit or command over massive distances. And today, we will learn how to do it. already know this. Your phone, your earbuds, your Wi-Fi box, they all talk wirelessly using electromagnetic waves. And light? Light is an electromagnetic wave too. It's the one you know best. You see it every day. Well, most of you do. Depending on the frequency, your eyes see it as a color. Violet for high frequencies and red for low ones. And for amplitude, that's the variation of brightness. Radio waves are the same thing. It's just a light that is invisible. And when you use an antenna, you are using a lamp, but for radio waves. A lamp that can also be a camera, because antennas can transmit and receive. They capture energy and turn it into an electric signal. That signal, we can represent it as a curve over time, maybe a sine wave, or a square one, or even a triangular one. You can vary its frequency, and if you want to analyze it, you can turn it into a spectrum, using the Fourier transform. Fourier, the goat, proved that every wave can be broken down into a sum, finite or infinite, of sine waves with different frequencies and amplitudes. Just like white light is a sum of all visible colors. Fourier invented the Fourier transform to decompose waves by frequency and amplitude. Plot that by amplitude and you get a spectrum, a visual representation of the signal's frequency components. On a spectrum, higher frequencies are further to the right. Stronger amplitudes gets higher values. To see how that changes over time, we use a waterfall graph. Spectrum scrolls top to bottom and the intensity is shown by color. That's kind of ironic since the color is frequency, not amplitude. With that, we can see how signals evolve over time. Because now it's time to talk about how we actually encode information into those waves. We have two types of telemetry, the analog telemetry and digital telemetry. In both cases, we use electromagnetic waves to carry the data. But what changes is how we encode the data onto those waves, and that's where the concept of the signals comes in. The wave is just a medium. It's what travels from the source to the receiver. The signal, on the other hand, is how we modulate that wave to send a message. With analog telemetry, we transmit a continuous value, theoretically with infinite decimal precision. But we live in the real world, a world full of noise, measurement inaccuracies, and imperfect components. So we get noise on our signal. And the weaker your signal, meaning the farther you are, the more that noise impacts the value you're trying to send. That's why nowadays we mostly use digital transmission. In digital telemetry, we encode values in binary before sending them, which helps prevent information loss. And from there, we've got an entire toolbox of modulation techniques. We can modulate in amplitude, frequency, and even phase. Yeah, phase. I haven't mentioned that one yet. Phase is the time offset of a periodic signal. If you take a sine wave at a fixed frequency and shift it by one full period, it's still the same wave, now shifted by half a period and it flips. And because a periodic signal is cyclical, we can represent the phase as a circle. An angle on that circle equals the phase shift. But hey, so far we're still on the easy stuff. Now, here's the problem. These simple modulations give us a pretty low bitrate. And the bitrate is crucial in telecommunication. It's the amount of information you can transmit per second. And if you possess an internet connection, you can now check your bitrate. It will be displayed in megabits per second or gigabit per second. Quick note. Here we're talking about the bitrate, bits per second, not the bandwidth, the width of the frequency range used. People confuse the two. They are related, but they are not the same. To increase bitrate, we use a symbol-based modulation, like QPSK. Let's say you want to transmit data on a given frequency. At that frequency, you can combine two sine waves in parallel. One on the I-axis, in phase, the other one on the Q-axis, quadrature, 90 degrees out of phase. Add those two signals together and you get a composite wave. And because you know the exact frequency of the I and Q signals sent in the composite transmission, you can separate them again at the receiver. And that lets us do something pretty powerful. We go from a one-dimensional signal in time to a two-dimensional signal in IQ space. We've added a whole new axis of possibility. By combining I and Q, you can place a point anywhere in this plane. We'll start by placing 4 points. Each point represents a symbol, and each symbol encodes 2 bits in this example. This point 0, 0, that one 0, 1, this This one here, 1, 0, and that one, 1, 1. The advantage? You've not doubled the amount of data you send, without increasing your transmission frequency or bandwidth. And we can go further, a lot further. You can add more points to the circle. You can stack multiple concentric rings by modulating amplitude. You can even create a full grid in IQ space. But be careful, the more symbols you pack in, the closer they get to each other, and the more likely noise is to mess them up. And you can't just boost your amplitude forever. We're still in the real world after all. In summary, more symbols equals more data, equals a higher bitrate, but less range because the signals become more sensitive to noise. Same things if you increase your bandwidth. You spread out your signal's energy so it sinks under the noise level. Moral of the story, it's tricky to want both long range and high data rate. But in model rocketry, you want both. You want long range, because your rocket is high up and moving fast, and you want decent bandwidth to send enough data per second. Enter the LoRa. LoRa, or LoRaWAN, stands for Long Range Wide Area Network. Originally made for long-distance IoT, for farming, weather station, and sensors in field, its little sibling, plain LoRa, uses the same principle, but point-to-point, from your rocket directly to the ground station. These little chips barely consume any power. They can run for days on a coin cell, they transmit at low power, but reaches insane distances. The world record? 823 kilometers, from a balloon using 868 MHz line of sight. They also exist in 433 MHz. Lower frequency equals longer range, but less data throughput, always the same trade-off. And you will ask, wait, how does it work? How does it go so far with so little power? And now you're thinking, what, that's like whispering across a metal concert and being heard on the other side of the pit? To understand, we need to go back to the spectrum. The LoRa doesn't need to use the phase, neither the amplitude. It uses the time. Each symbol is a sweep, a frequency chirp. Depending on the offset of that sweep, we get one of 128 possible symbols composing this LoRa transmission. The signals ramps up or down in frequency, and the shape over time lets the receiver recognize the symbols. Since noise is random and the signal is long, the shape stands out, even under the noise. That key parameter, it's called the spreading factor, stands for Long Range Wide Area Network. Alright, I did forget a little detail, and we will make sure not to do something illegal. And for that we will do a little course in amateur radio. I told you we couldn't blast power all over the place, but I didn't say why. Simply because it's illegal. When you look at a radio spectrum, it's just a beautiful continuous band stretching out to infinity. But to avoid a total cacophony, where everyone is sending data over everyone else, we had to create precise rules. In the free bands we've got 433.5 to 434.79 MHz up to 10 mW, 868 to 869.2 MHz up to 25 mW, 869.4 to 869.65 MHz up to 500 mW, and don't forget the Wi-Fi bands used by some XBs, 2.4 GHz, 5.5 GHz, etc. Anyway, choose the right frequency, the right power, or get ready for a visit from the Spectrum Police. Let's get back to the settings. The full code is linked in the description. Make sure to install the LoRa.h library. Inside the begin function, we set the frequency, 869.5 MHz, the frequency that lets us transmit the strongest, TX power, depend on the chip, up to 20 dB, which makes approximately 100 mW for those who use the watts. Now we have the spreading factor. It can be set set between 7 to 12, on Bellissima it was set on 8. Here we can also set the bandwidth, 125, 250 or 500 kHz. We went with 250 kHz. Here is the preamble length. It's the length of the synchronization sweep at the start of each transmission. The more length, the more likely the receiver can catch it. Finally, the IQ inversion. It flips the sweep's direction. Super useful when lots of people are on the same frequency, like at a launch campaign, or for full duplex communication, which is a two-way communication. Now your telemetry is tuned, right frequency, right power, and now we can make it say something. To build a working telemetry, you need to lay it out clearly. Visualize it as a schematics. Not something too complex, just a left to right flowchart of your telemetry electronic system. At the left you have your sensors. They send data to an experimental board, directly or indirectly using another board. That experimental board processes and logs the data to an SD card at the maximum possible speed, and it builds a packet, a frame, for the telemetry. Your experience board will gather the data before transmitting it to the telemetry. This gathering is called a frame. It is a set of information that your telemetry will send at once with each transmission. A frame is therefore a sequence of 0 and 1 grouped into 8 bits called the byte. At first glance, this series of bytes represents nothing, but in reality you have several pieces of information that are encoded differently on a different number of bytes. If you want to save integers, you can use int 8 or 1 byte, int 16 for 2 bytes, or int 32 for 4 bytes. For decimal numbers, you can use float 32, which are stored on 32 bits, but there are also half floats on 16 bits, so 2 bytes. You also have booleans, which in theory are supposed to be 1 bit, but be careful, the Arduino treats them as if they were on 8. You have to create special functions if you want to optimize them, and you can add a few special bytes at the start and the end to mark the frame boundaries. Now that we've seen how we're going to transmit the information, we'll still have two options for connecting the experiment to the telemetry. Either connect directly to the LoRa module, or add a microcontroller, for example an Arduino Nano, using another communication protocol, for example via an I2C bus. A little reminder, I2C frames have a size limit. You may need to reassemble the full message before sending it over the LoRa chip. To make your life easier, I recommend using an integrated board like ESP32 SX1262. Or, like me, you can use a dedicated LoRa chip, like the RFM95W. It transmits between 862 and 1020 MHz. Just hook it up according to the datasheet. Here's how I wired mine, directly on a custom PCB made with KiCad. Be careful though, the layout can vary depending on the supplier. I added voltage dividers, since the Arduino Nano uses 5V SPI, but the LoRa chip runs at 3.3V. It might not be necessary, but I like to play it safe. And since my ISO goes from the chip to the Arduino, you don't need a divider there. For power, I used the linear 3.3V regulator with two capacitors. A buck converter could work, but if it's too noisy, it will mess up your signal. For the antenna output, I used an SMA connector like the one used for Wi-Fi. Important, don't place a ground plane under your RF signal trace. This is really important. Carbon and aluminium blocks radio wave, so only fiberglass, plastic and especially no metal around your antenna. Otherwise, you'll be like conspiracy theorist, with aluminium foil on your head and you won't receive anything at all. This was for science. As soon as the signal leaves the chip, it starts degrading. Every millimeter of trace, every joint, every cable adds loss, noise and echo. Therefore, the chip to antenna path must be as short as possible, as straight as possible, as clean as possible, especially the soldering joint. Even with good coaxial cable, it hits the signal strength, so keep it short. On the ground side, it's simple. An Arduino Uno plugged via an USB cable into a long cable or a hub going back to the PC. That makes a nice little remote receiver setup. Attention, never power on your LoRa chip without an antenna. It can fry instantly, and even if it's cheap, you'll have to start over from scratch. Once your signal leaves the antenna, it weakens very fast. It spreads out in every direction. direction, and if it hits clouds, rain or trees, it gets diffracted, absorbed, scattered. Quick reminder, radio waves don't go through the ground. If your rocket lands behind a hill, there's no line of sight. You'll only get reflections if you're lucky. That's why on the ground we bring out the big guns, a Yagi antenna. It's a directional antenna. It picks up signals about 10 times stronger, 10 decibels, within a 30-degree cone around its axis. Remember, at the start of the video, we compared antenna to lamps. Some lamps shine in every direction, others focus their beam. Well, that works for reception too. An antenna doesn't just see everywhere, it can also listen better in a specific direction. The more focused the beam, the stronger the signal. Best examples? Parabolic antennas, and of course Yagis. They are built to focus the signal in one direction. Yagis are the one you used to see on rooftops. Well, in old movies, since broadcast TV is kinda dead now. On the other hand, a straight antenna, just a rod, usually emits in a torus shape, a donut basically. If you point it straight at the receiver, you get almost nothing. But on a rocket, that's not necessarily a problem. If your ground station is off to the side of the flight path, you can use the donut side and get a bonus of about 3 decibels, which is not bad at all. Anyway, we are not allowed to transmit any stronger, but we are absolutely allowed to listen as loud as we want. And since we are not limited by size, we might as well go big. That's also why NASA's ground antennas are massive. The probes have tiny antennas, but on the ground, no limits except the budget. And like at NASA, a good ground station can support multiple rockets or missions, and last 4 years across many campaigns. So if you're going to invest in one place, invest in your ground station. It will always come in handy. Now that we've seen the full journey of the signal, let's talk about a very useful tool to check if your transmission has any chance of making it to the ground: the link budget. We can calculate it using standard formulas, and with LoRa, it's convenient because we know roughly where the receiver sensitivity limits is. But nothing beats a good old real-life test out in the field, with your actual antennas in a real environment and all the chaos that comes with it. Once you've done all that, you need to check that it actually works. It's not uncommon to have terrible antennas, so testing is crucial. Even if you've calculated your link budget, nothing guarantees your Amazon or your AliExpress antennas are any good or not effective. First, you will estimate the maximum distance you will be from your rocket. Then, look at the elevation map around your area, or something like a topographic map, and with the help of Google Street View, find 2 spots with line of sight at that distance. To factor in weather issues, I recommend you to go for a slightly longer distance, just to be sure it will work on launch day. Then, split into 2 teams and use your phones to communicate while testing. Try out different telemetry settings and check the real performance.
Eh ben, on capte avec cette télémétrie 800 MHz.
I recommend testing once with just the transmitter connected to your PC to quickly pick the right setting, and then a second time with the full system install your rocket and power it on. Because if your rocket has metal or electronics, it also generates noise and your telemetry can be affected. You can use the packet RSSI function on the receiver side to measure signal strength at your chip's input. The closer it gets to -110 or -120 decibels, the closer you are to total loss of signal. Here is what it looks like on a real spectrum analyzer. Alright, you've got telemetry. It works, it transmits, and you receive it. What do we do with it now? Because receiving LoRa packet is nice, but reading, displaying, and saving them, that's even better. And for that, I've got 2 tools for you. First one, VisuAI. It's a Java-based app used during the Belisama flight. It lets you select a serial port, define the data type at each index in the frame, and display it all live in a custom interface. Plus, it saves everything as raw data just in case. It gets the job done, it's stable, lightweight, and built for its exact use case. And bonus, it's open source. Or, if you like getting your hands dirty, I've been working on a Python project. The idea? Connect multiple stations at once, store all received data in an InfluxDB database, and visualize it using Grafana, with raw backup as well, just in case. And maybe one day a 3D live display. But for now, it's just Grafana. Grafana is a super flexible tool. With a sleek interface you can fully customize. But I'll tell you right away, this Python Python project is not plug and play yet. The project is live, it works, but you'll have to dig it a little to get it running. If that sounds fun to you, all the links are in the description, and I'll make a short tutorial video soon. Now you've got a working telemetry. You've tested it and you can visualize the data. You're probably thinking, alright, we're good to go. Well, no, not yet. You're still one step away from running everything, as always.
Ah bah c'est bien, Neil, super pour l'appareil photo. T'es vraiment un sale petit.
Telemetry is tricky, really tricky, and kind of touchy too, especially when it's actually running. So let me give you a few tips, unless you want all this work to go to waste. Bottom line, just so you know, the tiniest things can kill your telemetry. I once fried a chip because of a deodorant, yes, an aluminium can. It was sitting on the desk, the signal bounces off it and shot right back into the amplifier's face. Same goes if you forget to plug in the antenna, or if a solder joint on the RF path breaks, or if you overheat the chip during PCB soldering. Bottom line, the best advice I can give is, once it works, don't touch it. Switch it off. No fiddling, just leave it to be. And speaking of switches, you've got a rule in your requirements which requires you to be able to cut telemetry at any time. A good month before the launch campaign, to give yourself time to redo things if needed, do a full test again, just to be sure. Once you're in place, after transportation, run another test. And obviously, during your probably multiple simulated flights for qualification, test it again. Let's talk about something crucial, the timeline. For those who don't know, the timeline is the full checklist to operate the rocket. For a simple launch, the timeline goes like this. Charge batteries the day before, go to the pad, turn everything on. But with telemetry, you've got a PC, an antenna, a tripod, cables, and in your case, an UPS. Because we wanted enough juice to stream the whole thing. Suddenly, things get way more complicated, especially during a simulated flight. And amid all that, don't forget the rockets. Once you're at the launch site, you're not done. It's actually just the beginning. Load everything into the truck, don't forget anything, set the rocket on the pad. Meanwhile, another team runs to the Jupiter tent to set up the ground station. Once everything is wired and ready, you turn on the rockets and check that the telemetry is coming through. In the end, your timeline will look more like a novel than a checklist. This is the real timeline from Bellissima. And since you will need tons of gear, I highly recommend making a packing list to make sure you forget nothing and know exactly where everything is stored. Best advice for writing your checklist and timeline? Do full rehearsal, multiple ones, way before the launch campaign, and write everything down. From cable connections, yes, one line per cable, to table setup, to powering things on, telemetry, gear list, everything. Do it as many times as needed, until you can do it under stress, in wind and rain, because that's exactly what it will feel on launch day. Speaking of launch day, once you've powered on your telemetry at the pad and the ground station is up, that's when you see if it really works under actual launch conditions. And if it doesn't work at that point, personally, I leave it alone. Maybe it's the metal structure of the pad blocking the signal, maybe we'll pick it up at liftoff, maybe not, but it's too late to panic now. Telemetry is a high-risk, low-reward game, so you'd better test the hell out of it and make it rock solid to give yourself the best shot possible. To wrap it up, I'd say telemetry is like a newborn. It's beautiful, complex, fragile, it's annoying, it never works, and sometimes it's terrifying. But once you love it, you take extra good care of it. That's it. A retext from 4 years of experience. Take it all in. And I know it sounds ironic, but my final advice is to make sure you have the maximum fun with your telemetry. Every time I've got my telemetry to work, I couldn't help but to think of that Einstein quote, "Key action at a distance." When Einstein said that, he was mocking the idea that atoms could ever be entangled. Which is ironic because in the end, he was wrong. And today we are just starting to use that kind of entanglement to transmit data. When I managed to get my telemetry to work from far away, I imagined the exact same thing. Me, just a tiny human, transmitting spooky action across gigantic distances. One thing is for sure, with this new telemetry and all the upcoming videos, okay, upcoming like 4 years from now, I'm definitely gonna have fun. Next video, it will either be about PID controllers and roll stabilization using reaction wheels, or Minute in the Sky IPSA edition. And I don't know if you've noticed, but a few things have changed. I love the name Taranis, the first real rocket, but it's not the clearest brand. So I've decided to make it all clearer. And I've also decided to create a training business. If it works, it could help me keep the channel running. Not to make quick bucks, but to make this project more sustainable. Here we see it clearly. Taranis is written on the side of the wallet, because it's a gift from one of my best friends. Because let's be real, this camera, nearly €1,000. That rocket, that's a solid 500. And this workshop in my apartment is also my rent. And right now, I do all this stuff with a full-time job on the side. I run the channel, the videos, the projects, and a regular life. So the goal of the company is to give the channel a real boost. And maybe one day, let me hire a video editor to get more videos out faster and not every 4 years. And let's be honest, at first it won't be enough. So if you can, feel free to support me by helping on Tipeee or grabbing a t-shirt. This isn't a donation drive. I swear, I'm never going to stop doing this. I mean it. But if you want to see these videos more often than once every 4 years, even a few bucks can help cover for videos editors, gear, and even 3D artists, and help blow up the quality and pace. Thanks for watching, thanks for your support, and see you soon for the next things we'll send together as close to the stars as we can.